Hi, everybody. Okay, I'm going to continue with the lab that we started in class and show you how to do curve fitting or linearization, sometimes we call it. So I have here topic 1, constant velocity motion. I usually assign this right in the beginning of the course, but I knew we'd have limited time to be able to do lab work, right? So like normally we could just do this stuff in class and get through it pretty quickly, but only being here every other day, this would have taken too long. So reading graphical methods. So I'm opening that up, all right, and what this does is it goes through um, how to run curve fitting. I guess it's a doc. I should probably make that as a PDF and put it back up there again so everybody can open it, no problem. But Google Drive should open it. But anyhow, it goes through a bunch of the stuff we've already talked about: independent variable, dependent variable, um, how to arrange your data in the graphs. Then it gets into this curve fitting idea. All right. When checking a law or determine a functional relationship, there's a good reason to believe that a uniform curve or straight line will result. The process of matching an equation to a curve is called curve fitting. All right. Anyhow. So it goes through and shows you how to write the equation like we did in class, y equals mx plus b. But then the slope of the line you have to determine to be 0.8 meters per second squared. So then the experimental equation is written like this, which we did in class for labs and stuff. So then it gets into, well, what do you do if you plot your data and it's not a straight line? What if it looks like this? This is known as an inverse function, right? So it says to make a test plot of 1 over v. So if you take all your volumes and you find the inverse of them, and then you plot pressure versus volume, you end up with a direct relationship. So it turns out that P was not proportional to V. P was proportional to 1 over V, the inverse of V. And then you write the equation of the line. P equals M times, now this is what's kind of weird, is the variable on the x-axis is now 1 over V, 1 over the volume. And basically you can see the slope of the line ends up being M, which, is something from thermodynamics, it turns out. But anyhow, if you multiply both sides by V, we just derived Boyle's law. Anyhow, if it's a top opening parabola, which looks like this, which is what our position versus time graph looks like, it says to square all the t values and then replot it. All right, so d is not proportional to t, it's proportional to t squared, which we sort of talked about in one of the classes today, because a quadratic follows a form of y equals ax squared plus bx plus c, right? So it's proportional to the square of whatever is on the x-axis. So how do we actually do this? Well, I know I have to square t, so if I square the time of all these data points, I should end up with a straight line. Now you might say, okay, let me just square all these and make a new column. Well, the computer can do it for you. You go data, new calculated column. I'm going to call it time squared. All right, the short name is t squared. You click this arrow, you can get a superscript. Superscript means it goes upstairs. And the units are seconds squared. Now, you would think if you're squaring time, it could square the units for you, but it can't. The software is not that smart. But anyhow, now we have to make the expression. This is like a calculator, basically. So I want to square the time value. So I find the variable time that was already generated from the video analysis, and I square it. And I do that by doing Shift 6 to make that little caret, like in your calculator. And I put a 2. So it's going to take the time column, that's what the parentheses are telling it to do, take the time column, square it, and put it into a new column called time squared, with the short name t squared and the units s squared. and you hit done, and it makes this new column here. Now you'll notice nothing changed over here. Let me just page auto range this real quick. So now, let me just make this look a little better. I'm going to go here and select the new one I made. Now it's important that you do these names right so you can actually find them. You know, you really don't be lazy when you make that new calculated column. I'm going to select time squared. Well, we see a much more linear line, right? So I put a fit line on this. Hey, not too bad. 0.998 correlation. So that correlation agrees with this. Pretty good. Now, it is a little bit curved, and you know, maybe the data would have come out a little bit better had I plotted every single point. Had I plotted every single point, I think the data maybe would have come out a little bit better. But, well, this is where we're at. I think maybe if I kill some of the early data here, so that kind of curves up in the beginning, I'm gonna grab that data, move it in a little bit. Yeah, that looks quite a bit better. Now, overall, the results here are okay. We'll talk a little bit about how we analyze this later on. So notice that here it was able to do Vx equals mt plus b, but up here it has capital X, which is the variable for position, equals mx plus b. Well, when you put something in for the short name that has a subscript or superscript, it can't put that in there for the name here. I think if I could also do it like that if I wanted to. Yeah, it won't change it there. So you have to be smart enough to know what it is that you are putting in there. All right, I know it's a lot of responsibility, but it's all right. All right, so that's how you linearize. Top opening parabola, which here tells me square the time. If there's a side opening parabola, you square the y variable. Those are really the only three we have: inverse, top opening, and side opening. We'll do full practice with this later on. But that's it for now. That's how you linearize it. We'll talk about the evaluation of data later on.